Good morning everyone. Myself G. Likta from CSIT and today's my topic is KVL and its applications. Let's see what is electric charge. The quantity of electricity that flows in a given time or is held in a component such as capacitor. The symbol to denote electrical charge is Q and its unit is coulomb. Charges may be positive or negative, like charges repel each other and unlike charges attract each other. What is electric current? It is the rate of positive charge flow. It is denoted by I and its unit is coulombs per second, that is amperes. I equals to dq by dt, where q is a charge and t is a time. Note, the current has polarity, that is flow direction. Electrical potential. Energy per unit charge expended in moving a charge from one place to another is called an electrical potential. It is denoted by V and its unit is volt, is nothing but joules by coulomb. V equals to dW by dQ. Here W is energy and Q is charge. And potential is always referenced to same point. Electric power. Amount of energy transfer per unit time. It is denoted by P. Its unit is watt, nothing but joules by second. P equals to dW by dt, that is Vi, and as a positive charge Q moves through a drop in voltage of amount V, it loses energy. Energy change equals to QV. Rate is proportional to charges per second. The ideal basic circuit element. Polarity reference for a voltage can be indicated by plus and minus signs. Reference direction for the current is indicated by an arrow. Example, resistor, capacitor, inductor, diode, etc. And its attributes are two terminals, that is points of connection, cannot be subdivided into other elements, mathematically described by its current, V and voltage relationship. A note about reference directions. A problem like find the current or find the voltage is always accompanied by a definition of the direction as shown in the image. In this case, if the current turns out to be a 1 mega ampere flowing to the left, we would say I equals to minus 1 mega ampere. In order to perform circuit analysis to determine the voltage in a circuit, you need to specify reference direction that need to guess the reference direction so that the answers may be in positive. However, sign convention example. Suppose you have an unlabeled battery and you measure its voltage with a digital voltmeter. It will tell you the magnitude and sign of the voltage. With this current, you are measuring VAB. The DVM indicates minus 1.401, so that VA is lower than VB by 1.401 voltage. And what is the positive battery terminal? Note that we have used ground symbol for the in given diagram. Often it is labeled as C for common. Sign convention for power. The passive sign convention for P, if we get P equals to Vi, then the current flows in the direction as shown in the diagram. If P equals to minus Vi, then the current flows in the direction as shown in the diagram. If P is greater than 0, power is being delivered to the gray box in the diagram. If P is less than 0, power is being extracted from the gray box. Power calculation example. Here is the example for power calculation. Circuit elements. 5 ideal basic circuit elements. Those are voltage source, current source, resistor, inductor and capacitor. And here voltage source and current source are active elements which are capable of generating electric energy, and resistor, inductor and capacitor are passive elements which are incapable of generating electric energy. Many practical systems can be modeled with just sources and resistors. Many practical systems can be modeled with just sources and resistors. The basic analytical techniques for solving the electric circuits with inductors and capacitors are same as those for resistive circuits. Electrical sources. An electrical source is a device that is capable of converting non-electrical energy to electrical energy and vice versa. Example, if we take battery, it converts electrical energy into chemical energy and chemical energy into electrical energy. Dynamo, generator or motor. It converts mechanical energy to electrical energy or electrical energy to mechanical energy. Electrical sources can either deliver or absorb. Ideal independent and dependent voltage sources. Circuit element that maintains a prescribed voltage across its terminals regardless of the current flowing in those terminals. Voltage is known, but current is determined by the circuit to which the source is connected. The voltage can either be dependent on a voltage or current elsewhere in the circuit and can be constant or time varying. Here is the circuit symbols for given. Other independent voltage Source symbols. Realistic voltage source. A real-life voltage source like a battery or the function generator in lab cannot sustain a very high current. Either a fuse blow to shut off the device or something melts. Additionally, the voltage output of a realistic source is not constant. The voltage decreases slightly as the current increases. We usually model realistic sources considering the second of these two phenomena. A realistic source is modeled by an ideal voltage source in the series with an internal resistance, that is Rs. Ideal, independent and dependent current sources. Circuit element that maintains a prescribed current through its terminals regardless of the voltage across those terminals. Current is known but voltage is determined by the circuit to which the source is connected. The current can either be independent or dependent on a voltage or current elsewhere in the circuit and can be constant or time varying. Here are circuit symbols for those. Electrical resistance. Electric field is proportional to current density within a resistive material. Thus, voltage is proportional to current. The circuit element used to model this behavior is the resistor. Here is the symbol and its unit is ohms. The current flowing in the resistor is proportional to the voltage across the resistors. V equals to IR, where V is voltage, I is current and R is resistance. Electrical conductance. Conductance is the reciprocal of resistance. Symbol is G and its units is Mohs or Siemens. Short circuit and open circuit. Short circuit, R equals to 0. No voltage difference exists and current can flow as determined by the circuit. Open circuit, R is infinity, that is no current flows. Voltage difference can exist as determined. Circuit nodes and loops. A node is a point where two or more circuit elements are connected, and a loop is formed by tracing a closed path in a circuit through selected basic circuit elements without passing through any intermediate node more than once. Kirchhoff's law. Kirchhoff's current law. The algebraic sum of all the currents entering any node in a circuit equals 0, an expression of the conservation of a charge. KVL. Kirchhoff's voltage law. The algebraic sum of all the voltages around any loop in a circuit equals to 0 as a result of conservation of energy. Using Kirchhoff's law, that is KCL, Kirchhoff's current law, considering a node connecting several branches as shown in the figure. Use reference directions to determine where the currents are entering or leaving the nodes and concern about actual current directions. Alternative formulation of KCL. Formulation 1. Sum of current entering node equals to sum of currents leaving the node. Formulation 2. Algebraic sum of currents entering node equals to 0. Currents leaving are included with a minus sign. Algebraic sum of currents leaving node equals to 0. Currents entering are included with a minus sign. And charges stored in the node are 0. A major implication of KCL. KCL tells us that all of the elements in a single branch carry the same current. We say these elements are connected in series as shown in the image. Current entering node equals to current leaving the node. I1 equals to I2. Here is the image for the KCL example. Generalization of KCL. The sum of currents entering or leaving a closed surface is 0. Circuit branches can be inside this surface, that is, the surface can enclose more than one node. This could be a big chunk of a circuit. Generalized KCL examples. Using KVL, that is Kirchhoff's voltage law, consider a branch which forms part of a loop. Voltage drop and voltage rise. Use reference polarities to determine which and where the voltage is dropped with no concern about the voltage polarities. Formulation of Kirchhoff voltage law. Sum of voltage drops around loop equals to sum of voltage rises around the loop. Algebraic sum of voltage drops and loop around the loop equals to 0. Voltage rises are included with a minus sign. Algebraic sum of voltage rises around the loop equals to 0. Voltage drops are included with a minus sign. This is about the conservation of energy. Look at the first sign you encounter on each element when tracing the loop. A major implication of KVL. KVL tells us that any set of elements that are connected at both the ends carry the same voltage. We say these elements are connected in parallel as shown in the image. Applying KVL in the clockwise direction starting at the top, VB minus VA equals to 0, that is VB equals to VA. Let's see the example of the KVL. An underlying assumption of KVL. no time varying magnetic flux through the loop, otherwise there would be an induced voltage, that is Faraday's law. Note, antennas are designed to pick up electromagnetic waves. Regular circuits often to do so undesirably, and avoiding these loops. Resistors in series as shown. Equivalent resistance of resistors in series is the sum of individual resistance, and it is the voltage divider formula. When can the voltage divider formula be used? Resistors in parallel. Consider a circuit as with the equivalent resistance. Here the KVL tells us the same voltage is going across each other. General formula for parallel resistors is its inverse sum, and here is a diagram for it. Current divider, Vx equals to I1 into R1 equals to ISS into R equivalent. Generalized current divider formula is given. Thank you.